Well, thank you. Okay, yeah, I am Jim Weirich. I'm the chief scientist for EdgeCase, which means I do whatever they tell me to do, actually. The title of this talk is A Critical Look at Fixtures, and I think it was Greg this morning started off with asking the question, who here likes fixtures? And no one raised their hand. So, why? What don't you like about fixtures? So this is your turn to participate.
Global data.
Global data, okay. Anything else?
It's out of your work stream. You gotta go look somewhere else and see it.
Okay.
They can be brittle.
They can be brittle.
It doesn't pass through models, so you lose logic, and you can put in bogus data really easily.
Okay. Doesn't pass through the model, so it doesn't go through the logic. You can put in bogus data really easily. Yes?
Building up chains of relationships is really awkward and foreign to the normal workflow.
Okay, building the relationships is awkward and foreign to the normal workflow. Anyone else? Let's just dump on fixtures right now, okay? It's okay. It's okay. Just kind of let it flow.
It's YAML instead of Ruby.
Okay, now we're getting down to the nuts and bolts. Okay.
You have to type. I hate typing.
You have to type. Yeah, okay, yeah. Too many keystrokes. Okay. Anyone else?
Each instance wants to be named.
I'm sorry?
Each instance wants a name line.
Oh, yeah, we need every single instance in it. Yeah. Hey, you know what? I think naming is one of the hardest things in software development. Okay. So, this is where I insert the apology, because I'm not here to talk about fixtures at all. I submitted a proposal, and the organizers came back to me and said, that's a really interesting talk, but it sounds rather Ruby-ish, and this is kind of a Rails-centric thing. Can you come up with a Rails topic? And I said, well, I'll just kind of wrap my talk around fixtures and kind of talk about what I want to talk about, and then and apply it to fixtures and see how it works. So really, I'm not really here to talk about fixtures at all. And that's why if you look at the abstract in the program, it doesn't say anything about it, because as I kept working on this talk, the talk kept changing on me. And I couldn't write the abstract until after I give the talk to find out what I really said. So this is really what I want to talk about. If you're familiar with physics at all, you understand there's certain fundamental forces in the universe. There's the strong nuclear force, the weak nuclear force, the gravitational force, and electromagnetism. And they're all kind of governed by separate equations. And what physicists would love to come up with is the grand unified theory, explaining all the forces in the universe in one simple equation. And no one has really been able to do that yet, although they've made certain attempts. And I think the same problem kind of exists in software these days, that we have lots of theories on how to develop software, but we don't have any grand unifying thoughts to put into that. And I was pairing, actually just this past week, and I was debugging a problem in our project with my pair partner, and we pulled open one of our methods, and we looked at it, and we both said, ugh. It was a gut reaction right here. When we looked at that code, we said, this code is terrible. I hate it. In fact, if you look in the comments, whoever wrote that, whoever was in that method last, and I'm not naming any names here, left a comment, refactor, because I don't like the way I'm doing this. So that was an easy clue. And we looked at that, and the problem was it was a model method. It was a method in one of our models that took a params hash and passed the params hash directly into the method and parsed out the data in the params hash and did something with it. I don't know if that bothers you, but that bothered me big time. I had that gut level reaction to that. Now, why did my gut react like that? What I would like to do, we train our guts by looking at code and finding out what works and what doesn't work. And what I want to do is get away from, the gut level reaction, be able to put into words what is wrong with doing things like that in that particular method. So I've been thinking about this for a really long time. And I'd like to come up with a set of principles. Now, if your principle is like a fundamental law or a governing idea that kind of defines and shapes the way we do software development. And there's a lot of people who've put together some rules or principles out there. Solid, that's from Bob Martin, his 5 principles of class design, single responsibility, open-close principle, Liskov substitution, interface segregation, and dependency inversion, I think are the 5 things that form the initials of solid. Actually, great principles to start with. The law of Demeter, or some people like to refer to it, the very good suggestion of Demeter. Dry, keep your code dry. That's a good one. I love that one. And we're going to see that one crop up a little later in the talk today. Write small methods is another principle. Designed by contract by Bertrand Meyer. I spent about 3 years playing around with Eiffel and love design by contract and the concepts that are in that brought forth. But I'm looking for some kind of unifying principle behind all of these things. Can we get to these things with some unifying ideas? When I first started in software development, right out of college, I worked actually here in Florida, over at Cape Canaveral, writing software for radar, collection of radar data for the launches at NASA. And my mentor at that job handed me this book and said, read this is a good book. And I don't remember a whole lot out of this book except for one thing. He addressed 2 basic principles called coupling and cohesion. Cohesion is how well together your software fits, how related they are to each other. Coupling is how different parts of your program relate to each other. You want high cohesion within your modules and low coupling between your models. I'm not going to talk much about cohesion today, but I want to concentrate on the idea of coupling because I think this book is a start in the right direction. If we're looking for some basic principles, I think coupling is one of the biggest issues in software development we have to deal with. And a lot of our principles deal with how to decouple our one piece of software from another piece of software. So, Glenford Myers in his book talks about 7 layers of coupling, 7 levels of coupling, and gives them names. They range from, at the bottom, the strongest coupling, up to the top where you have no coupling whatsoever. 2 modules are not coupled if a change in this module over here has no effect on this second module. So it is entirely possible to write modules that are non-coupled. It's probably impossible to create an application out of totally decoupled modules because they do have to talk to each other and communicate with each other somehow. So you got to couple them together, but you want the coupling to be lightweight. Down at the bottom, the most tightly coupled type of coupling is called content coupling. And essentially, that's when you reach into the innards of a module and rip it apart and do something internally. Violating private would be content coupling. Monkey patching probably is, depending on the type of monkey patching, is probably content coupling. So, that's probably the worst kind of coupling you can have. So, that's the extremes there. What's the stuff in the middle? Let's concentrate on these 4. And I'm just going to go over these briefly because I think they're good ideas, but I think we need to expand beyond these. These 4 here are looks at 2 different things. First of all, they're grouped into local data and global data. Someone said over here, I think it was you, said global data fixtures. That's why you don't like fixtures, because they are global data. According to Glenford Myers, when 2 modules share something that's global, they are very highly coupled together because they cannot work without that global thing being there. If they share local data, that would be like passing parameters into a method. That would be local things just shared between the 2. Nobody else knows about that data, and it's private between them 2. That would be local data. The other differentiation then between the finer differentiation between these 2 is based upon simple data versus structured or more complex or composite data. If you have 2 modules that are merely connected by a method call that passes simple primitive data like integers or simple things like that, that's fairly lightweight coupling. If they pass data that has more structure to it, if you're passing domain objects like user objects or things like that, that's a little tighter coupling between them. So Glenford-Myers distinguishes between that. And truthfully, this stuff comes out of the 70s when you didn't have a lot of object-oriented design going on, and the structures you pass are actually layouts of physical memory that you pass back and forth. So that's even tighter coupling whenever you go to structured like data. And of course, there's the same distinction with global data as well. The final level of coupling is called control coupling. And this one's kind of interesting because the others, you could actually write a little analyzer to analyze your program and determine whether it's one of the other 6 kinds of coupling. But control coupling is more about intent than about the actual passing of data back and forth. Control coupling happens when you have a method and you pass a flag into that method. And the flag tells the method what to do. It directly controls the algorithm that the method is using. Symptoms of this: if the method's description has the word or in it, or something that's semantically equivalent to or, doesn't help to just rewrite the description to use a different word. Something that's semantically equivalent to or, and also the flag value that you pass in is arbitrary. It has no domain meaning whatsoever. It's just got the meaning that you decide to pass in. Example of this is array instance methods. What does this method do? Depends, thank you. It returns a list of instance methods for the array class. Which instance methods? Well, it depends on whether you pass in a true or a false. One of these returns a list of all the instance methods available in the object. The other version of this returns the instance methods that are defined directly in array and ignores the ones in the superclasses of array. Now, which one's which? Quick, tell me. Yeah, you've done this enough that you know, but there's nothing inherent about true versus false that tells you it should be all the methods or just the immediate methods. This is a case of control coupling. Your program would work exactly the same if you rewrote these into 2 separate methods and just called them separately. There's rarely a case where you need to pass in true or false in as a piece of data. Also, the description of this method is telling. The instance methods in module are returned, otherwise the methods in mod and mod superclasses are returned. And I will claim that otherwise is semantically equivalent to or for this description. So control coupling. Control coupling is kind of in the middle. Sometimes it's useful to have, sometimes it can be detrimental. Here's another example of control coupling, and this has a kind of different effect. The finder methods in Rails. The first parameter you pass in is a control parameter saying find the first method or don't find the first method, find the first instance in the database or find all the instances that match this particular condition. It's control coupling. Now, the interesting thing is not only is a control coupling being passed in, but the data coming out of the method is entirely different. If I pass in first, I get one object. If I pass in all, I get a list of objects. So if I were to make this first parameter a variable that was being passed in, I would not know how to handle the output of this method unless I looked to see whether it was a first or an all. Or unless I look to see if it's a list or not. The data coming back depends upon the parameter being passed in. Again, you can change this to find first and find all, and it had very little effect on the rest of your program. Control coupling. Okay. These classifications from Glenford-Myers are okay. I use them and I lived by them for a number of years, but I found that when you got into object-oriented design and object-oriented language, and specifically dynamic languages, these kinds of categories tended to fail. Especially with dynamic languages, structured data is not a layout in memory that's hard to change. Structured data tends to be messages that you send to Ruby objects that return things. So the stamp versus data coupling distinction in Myers was not nearly as strong as it would be like in C or in Pascal or the languages that Myers was originally working with when he came up with those distinctions. So I was still looking for something a little more fundamental than these classifications. This is a good book. Now let me rephrase this. This is a good 1/3 of a book. This book, what every programmer should know about object-oriented design by Mueller Page Jones, is written in 3 sections. The first section is a fairly decent introduction to object-oriented design. Now, if you're new to OO, it's worth reading. If you've done some OO work before, the introduction, you're not going to learn anything from it. So, the second part of this book is an introduction to a notation for writing graphical designs, kind of like UML. But this book was written before UML was popular. So Mueller Page Jones introduces his own notation that nobody uses. So the second part of the book, you can skip that and you won't lose anything. The third part of the book, however, starts off with a discussion of design principles for object-oriented designs. And this part is well worth the price of the entire book. If you skip the first 2 sections and read that third section, the book is worth it. And what he does is introduce a concept called kinesis. Now, I really like the word kinesis because when you say it, people say, huh, what? And it's fun to say, it's fun to pronounce, and you get puzzled looks from people when you say it. So, I challenge you today to interject the word kinesis into your day-to-day conversation. Kinesis merely means things that are born together and grow together. They change together. And this is exactly what we're talking about in our designs. We have pieces of software that are related to each other. And when I change module A over here, module B needs to change in correspondence to that to keep them in sync. So kinesis in software is when 2 pieces of software, 2 elements of software design, change when one requires a change, the other also requires a change. They share kinesis at that point in time. Let's make this concrete. Let's give an example of that. Suppose you have this code right here. You've got a model object called customer, and it has a method called email in it. And email does something. We don't care what, so we just kind of left that part out. And you have another piece of software over here that uses the customer email in some interesting way. What is the kinesis between these 2 pieces of software? Email. They both refer to the name email. One defines the meaning of email, the other uses the name email to invoke the original definition. So these 2 pieces of software share a kinesis that is based upon the name email. And we call this Kinesis of Name. We're going to go through several different kinds of kinesis. But name is probably the most, don't want to use the word most, it is the least connecting of kinesis. It's probably the one kind of kinesis you're going to strive for when you're dealing with separate modules. Kinesis of name is probably better than most of the other kinds of kinesis. And we'll see that as we go along. So, if I rename the method email, I have to rename every place it's used. So the original definition and every use share a kinesis of name between that. And we see that on the refactoring browsers. That you have the refactor method that changes all the method names and the related uses of them. Okay. So, kinesis of name can exist between your code and things that are not code as well. Such as, well, this is the schema. I guess it is code in this example, but in the schema there exists a field that is email. And if you change it there, you're going to have to change it everywhere it's used, or you're going to have to change the user module to map it correctly. You're going to have to do something. So there's a kinesis of name between not only the code, but also the database schema as well. Okay, is there any other kinds of kinesis in this example? Customer. These two right here? Actually, I will say no. If I rename customer, will the other code stop working? No. So actually, there is no kinesis of name in this particular example. Now, I might want to rename it. If I radically rename it to something semantically different, I might want to go through and change it, but it's not, that's kind of a soft relationship. It's not the hard relationship where the code breaks if it changes. So this is not at least not a hard example of kinesis of name. However, there still is one other piece of kinesis in here, and that's here. The parameter name being passed in is used immediately in the body. Well, you say, but it's in the same method. Exactly. Kinesis within a method can happen as well. Between lines of code, kinesis is any piece, any element related to another. And if one changes, the other has to change. So if that first line changes the name, the second line needs to change as well. So you have kinesis within a method as well as kinesis between methods and between modules. Interesting. So this shows us that locality matters. Turns out that if I have a bunch of code in a module, the module's kind of self-contained, the kinesis within that module is probably going to be kind of high, because they're all working with the same things, they're all reusing the same names, and they're working together, they're designed to work as a unit. I will tolerate a higher kinesis within the module than I will tolerate when kinesis with pieces of software outside the module. So I want my internal kinesis, it's okay to be high, or at least it's not as bad if it is high. But the kinesis between that module and other pieces of software, you want to have as low as possible. So I call that the rule of locality. As the distance between the software elements increases, you want to choose to use weaker forms of kinesis. Okay, so locality. Other kinds of kinesis. I was working with a piece of software just the past week, actually, where we took a list of params off of a web form. They came back as a hash. The hash was a ID pointing to a checkbox value, something like this. And I turned this into a list of pairs, where I would find, say, an order by the ID, and then the value would translate, in this case, let's say it's perhaps an expedite flag. We want to expedite this order, this other order doesn't need to be expedited. So I passed in, I turned that orders list into an array of pairs. Then I passed the pairs down into the model. So process order, we get a list of pairs. We iterate over the list of pairs. And for each iteration, we'll get the order, we'll get the expedite flag, and then we'll handle them in whatever manner. Now, what kind of kinesis is between these two pieces of code? This is called kinesis of position, because the position of the items in that pair is important. If I swapped the flag and the order object in the pair, I would also have to swap the order that they're declared where I handle them. So there's a kinesis there. It's not determined by a name, but it's determined by an absolute position in some kind of structure. So this piece of software, the piece of software that builds the ordered list of pairs, and the piece of software that processes the list of pairs has kinesis of position between them. Now, I was actually okay with this. Passing in a list of pairs seemed fairly easy, fairly low overhead, and I was quite happy with just doing that. But consider this. What if instead of having just 2 items, I had 6 items? Did anybody's gut just kind of go, ah? I will claim that a pair, a list of pairs, has a low degree of kinesis of position. However, when you start adding more, definitely at 6, I would start revolting. Probably at 3 or 4, I would probably start objecting to code like that. So kinesis of position has this idea of order with it. Once I reach this many, I probably would not use an unstructured list to hold the data. I'd switch to something like a class or a struct or even a hash table. Probably, as the number of items increased, I'd start with a hash, and when I got more items and when logic started needing to be added to it, we'd switch to a struct or a class itself. So there's this kind of hierarchy of a low degree of position and a high degree of kinesis of position that forces me to make different choices in my software. So here we have a refactoring, a replacement of kinesis of position with what? Now all these fields are named, and I refer to them by name. They no longer matter where they are in some kind of absolute position, but since I'm referring to them by name, I now have kinesis of name. So I've converted a high degree of kinesis of position into something that is kinesis of name instead. So there's some relative values between these two things. So degree matters, and I will claim that kinesis of name is a smaller kinesis than kinesis of position. Because position, that changes, and it's kind of, there's a high degree of coupling with that. Anybody disagree? Okay, good. You're all on board. Excellent. So, rule of degrees. If you have a high degree of kinesis, you want to translate that into some kind of weaker form of kinesis if possible. So, okay, another example of kinesis of position. Suppose we wrote our finders like this. Our finder had a condition and an ordered by parameter. That's probably okay. And notice that the position of the orders in a parameter list have to correspond to the order that you pass it in when you call. So there's a kinesis of position with standard parameter lists in Ruby. And this is also why 1 parameter, 2 parameters, 3 parameters don't bother me. 4, 5, 6, 7, 8 parameters do bother me. And it's that degree of kinesis of position with parameter lists. If you had a lot of things you were passing into a method, conditions ordered by the limit, the offset, the selected fields, all this stuff, you do exactly what Rails did when they defined the finder, is to switch from kinesis of position to kinesis of name by introducing a hash with named fields. I'm really liking this idea of kinesis. Do you see how it kind of keeps cropping up in the stuff that we already know and kind of validates decisions that we've already made? I really like this idea of kinesis. Okay, another example of kinesis of position. Oh, this one hit us the other day. In a lot of our tests, we needed a worker object, a staffer object, or I guess in this case it's a user object for the test. And the user object just needed to be there because you needed to have a user when you did something. But we didn't care what user it was, just any old user would do. So we had a lot of code that started their tests like this. Just find the first user and give it to me. And that worked fine. Until we added roles to our program. And certain users could do certain things. And certain users could not do certain things. And if you grabbed the wrong kind of user to perform an operation, then you would get a role privilege violation on that. So we started having random failures depending on whose machine it was running. It would work on my machine, but it wouldn't work on my coworker's machine because their database returned a different first developer. Kinesis of position. Whatever happened to be first in the database, that's kinesis of position. Again, how do you fix it? Go from kinesis of position to kinesis of name. Find the user you want and make it explicit. Cool. one piece of our app, we have this funky tri-state. It's not a radio button, it's kind of like two checkboxes that are coupled to each other, that they can both be off, or one or the other can be on, but they can't both be on at the same time. So we implemented them as two checkboxes with a little JavaScript to connect them to make sure that only one was on. And what you get back from that is going to be the ID of that checkbox with the value that is returned. And we map the value 1 into the given flag and the value 2 into the not given flag. And if it's not there, it's the unchecked state. So we handle it like that. The code that processes this might look something like this. If you pull out the params, if it's a 1, we mark it as given. If it's a 2, we mark it as not given. This is called kinesis of meaning, because we have assigned arbitrary meaning to literal values in our program. There's no intrinsic reason why 1 means not given and 2 means given. We just decided that's what it's going to be. Now, this is kinesis, because if I change the checkbox literals, I have to change everywhere that it's used. And this is not a good thing. This is a high level of kinesis between these two elements. So what do? When you have a high level kinesis, you want to reduce it, you move to a lesser, a weaker form of kinesis. Kinesis of name being my personal choice. So if we introduce a couple constants and then use those constants in the form and then in the code, we've reduced the kinesis of meaning to a kinesis of name, because now we're referring to particular names again. And I can change the values all I want, and there's no effect. As long as I keep the names and don't change the names, they're okay. So that's kinesis. So we've reduced it to kinesis of name. But what's really interesting about this example, where I had kinesis of meaning between two elements, when I switch to kinesis of name, I have kinesis of name between 3 elements. So it's a weaker form of kinesis, but it's connecting more pieces of the code. So there's a trade-off. That's why a lot of times we don't move to this until it's used in multiple places, because the incremental advantage of doing this is lessened. Okay. Let's go back to this example. There's an interesting kinesis between these two lines of code. Particularly the values I select. Most kinesis is involved with making sure things are consistent. That if I change something over here, I have to change it likewise over here. In this case, it's that I have to choose different values for each of these things. I can't choose one for both of them. So once I choose one for med given, I cannot again choose one for med not given. So there's a connection between these two, and we call this contranasence. It's not connasence, it's contranasence. And this is kind of a trivial example. Okay, can't choose one. But there's other examples of contranasence. And we see this cropping up all the time. Suppose I write an XML library, and I define a class called node. And you're writing a graphing library. And you're going to create a tree-type graph of nodes. And you have a class called node. We have contranasence between our choice of class names. You cannot choose the same class name as I choose, because we're sitting in a global thing and they conflict with one another. Now the easy solution, Ruby has an easy solution to this, right? And everybody does this, right? You always put all your classes within a module. By bearing them within a module, we now have no conflict between my choice of node and your choice of node. Of course, we just kind of pushed the whole problem set down one level, because we still have contranasence between our module names. But that's usually easier to deal with. You have fewer modules than you have classes, so That's an easier choice. So that's a good thing to do. Contra-nasis means that we need to use namespaces. Again, another good software engineering principle that comes out of the concept of kinesis. And why did I pick the class node? Because Ruby already has about 8 different class nodes already, and each of these are in their own module, so there's no conflict between them. Okay, another example of contra-nascence. Suppose I decide that I want to convert some arbitrary object to XML. Oh, excuse me, to a node. In my XML library, I want to be able to convert it to a node. Now, this is kind of a silly example, but this actually does happen in practice. So I go into kernel and I create a 2-node in there. You go into kernel and you want to do the same thing with you. We have contra-nascence between the method names that we put in global objects. And this is a problem because we can't fall back to namespaces to resolve these errors. So we have to be very, very careful when going to global classes and adding things to things that everybody shares. In general, don't do that unless there's a really, really compelling reason. And if you have a compelling reason, be very careful, put checks around it, make sure no one else does it, and at least give a warning when that happens. So, contra-nasis appears in that. Now, selected namespaces is a solution to all this, where you can put methods within a namespace within an object. That's supposedly going to happen in Ruby 2, but nobody knows what it's going to look like. No one's really clear on exactly how to implement it, so don't hold your breath for that. In the meantime, just be really careful about doing stuff like that. What are you doing here? Okay, we've got about 15 minutes left. Suppose we're working in an application and we want to create checksums on a string of digits. Suppose we're generating some maybe user numbers or something and we want to add a check digit to it so it's not easily corrupted. And this is a real simple checksum right here. In this case, if we have a string like this, we add an 8 to it. And the algorithm is take all the digits, add them up, take it mod 10, and then add a check digit that'll bring the entire checksum and the entire string to 0. It's a very simple checksum type thing. So we have a method called add check digit that adds a check digit to the end of a digit string. We have a method called check that will validate true or false if a string of digits is properly checksummed. So here's the code for that. Just give you a second to digest that, but essentially what we're doing is just what I said. We take all the digits, split them up, run a little inject loop that adds up their totals, and we take it mod 10, and that becomes a checksum. And then we calculate the correcting digit by subtracting the checksum from 10, taking that all mod 10, converting it to a string, and just appending it to the end of our digit string and returning that value. So add checks digit is very easy. The check algorithm down here does the same thing, calculates a checksum, and just make sure that the checksum is 0. So it's a pretty straightforward loop. There is a kinesis, though, between these two pieces of code. And that kinesis is called kinesis of algorithm, because the two pieces of code must agree on the algorithm being used to calculate that checksum. Now, this is a really trivial and silly checksum method, true, but it illustrates the point. They have to agree. If I were to update this to use some fancier cryptographic method, I have to change both places. And actually, the duplication here is a little bit bothersome. I'm doing the same thing twice. There's kinesis of algorithm. So what do you do when you have a high level of kinesis and you want to reduce it to a lesser, weaker form of kinesis? Introduce Kinesis of Name. Let's name that algorithm checksum. We write it here in its own method, and then we use it in both places. We have the advantage that these now read a lot better than they did before. plus we have the algorithm located in one spot that's referenced by the name of the method. So again, we have reduced Kinesis of algorithm to Kinesis of name. That's kind of cool. It's also called the dry principle. So I will claim that the dry principle is based upon kinesis. The idea is based in kinesis. I'm really liking this whole kinesis idea. Okay, so there's other forms of kinesis. A really cool one is kinesis of identity, where two pieces of code have to reference the same object. And that becomes an issue sometimes in Rails programming, where Rails won't always return the same object for two different lookups. And that can cause problems occasionally. I know we've ran into it in our application. So kinesis of identity, there's kinesis of type, several others that I'm not going to go into right now. But let's get back to fixtures and apply what we've learned, these kind of base level ideas of kinesis against the idea of fixtures and see where that gets us. So here we have an old style fixture file. Nobody writes fixtures like this anymore, thank goodness, because of what we already know about kinesis. What is in here? What kind of kinesis do you see in this fixture file right here?
Name and position, contranesis, and probably others.
Okay, kinesis of name, where is that?
Just that you have to reference them by name elsewhere.
Okay, the name of the object is there, and you have to reference it there. Kinesis of position, elaborate on that one.
They might go in the database in a certain order, possibly, or you're explicitly picking ID.
We're explicitly picking IDs, so that is definitely kinesis of position. Here's the first one, here's the second one, and we use those in determining the roles. This is why everybody hated fixtures to create relationships, because you depended upon kinesis of position, where when you have one or two, that's okay, but if you got a whole file of fixtures, keeping all those positions, those IDs, straight in your head was an onerous job, terrible. Okay, any other kinds of kinesis in this file?
Yeah. Algorithm.
Kinesis of algorithm, where at?
Hash.
The password hash. That password hash is calculated by a certain algorithm. And I just stuffed a random string in here. If we change the algorithm, we're going to have to change the string. So that is kinesis of algorithm. Very good. So fixes for this. Obviously, go from kinesis of position to kinesis of name. Newer Rails allows you to do this, where you reference the role by name rather than the ID. You can drop the ID so you no longer care where these things are in the database. You can use the ERB style calculation here. So we put the algorithm right here in the code. And I'm just using crypt, but probably you'd want to write your own method, name it yourself, and have control over what that algorithm is there. And you'd use that there. Now when you change the algorithm, you don't have to change the fixture files as well. Okay. So that kind of fixes up a lot of our problems with positions. We've reduced everything to kinesis of name now. However, what else is bad about fixtures? And Nathaniel, you can say it again.
Global data.
Global data. We're still dealing with global data. And the whole idea of locality. I don't know how much, this hits me all the time. I'm testing finders, and I want to make sure that my finder finds all the workers. So I have a special finder method that finds all the workers, and we validate it by checking the number of workers in that fixture file. And I know it's 2 because I wrote the fixture file and I set the test equal to 2, and the test passes. And then weeks later, I'm writing another test, and I need a different kind of worker. And so I add a new worker to the fixture file, and my finder test fails because there are no longer 2 workers in the file. There's 3 workers, and it fails, and it's totally unrelated to the test I'm doing. So I get this test running, I run all my tests, and other tests are broken. Now this is not too bad, but when your finders are very specific, I want to find all the users in this file whose birth date is within this span, who's ordered such and such a material. When you got finders that are very detailed like that, the kind of finders you really want to test, Just about any change to the fixtures, adding a new instance in the fixtures, will break those kinds of tests because it'll change the numbers of things returned from that. So how do we get around the global nature of fixtures? Okay, solution? Turns out there's lots of solutions. And I'm not actually even going to talk about the solutions that say, hey, there's fixture scenarios where you can customize fixtures for a given test. There's things like Factory Girl. There's Foundry, which I just started playing with from Jeremy McAnally. That's kind of cool. It's kind of a DSL for defining fixtures. In our project that we did, we actually rolled our own where the fixture replacement, we create data through a set of definitions that say, okay, if you're creating a database object, you do it like this. If you're mocking it, here's the kinds of things you also want to mock in addition to that. So we can easily create a mock or a real object based upon data that we're storing elsewhere. So it's not hard to do. The key is to move the creation of the data out of the global fixture file and move it locally to your test. So now I've kind of come full circle here. We started with fixtures. We went out into this rant about software engineering and kind of came back down, kind of seeing that these ideas of software engineering, these ideas of kinesis and modularity kind of feed back into what we already know. And I'm thinking, and I want to play around with these ideas some more. Here's some of the other fixtures that we've mentioned. Kinesis of type means they have to, two software pieces need to agree on the type of the object they're working with. There's a distinction between static and dynamic kinesis. We talked only about static. Static kinesis can be determined by physically examining the code base. Dynamic kinesis happens at runtime and deals with things like timing. Kinesis of execution is what gives rise to race conditions in multi-threaded code. So again, this whole basis of kinesis, I think, is a good foundation for understanding why we like certain things in software and why we don't. This is up on GitHub under my account. It's called presentation_kinesis. If you want to download and grab this, there's a whole bunch of books in here that I will highly recommend. What Every Programmer Should Know About Object-Oriented Design by Miller Page Jones. He rewrote it later. It's the same book, but with UML instead of his funky notation. So either one is good for that. Likewise, Glenford Myers seemed to write that same book twice. Again, Composite Structure Design and Reliable Software Through Composite Design. Kind of the same book, kind of different focus between them. Other books that we haven't really gotten into, but the solid principles are in the Robert Martin book. Bertrand Meyer has all kinds of good software engineering principles that it's well worth a read for that. And of course, Pragmatic Programmer, just some really practical advice for dealing with software. And thank you. Any questions? We got just a few minutes. Yes?
Since you're talking about fixtures, I have a question about fixtures. If you're dealing with an application which is pretty much a 50-50 split between Rails and a very rich front end and Flex and Silverlight or something, and you feel that you need to test the front end as well, would you recommend still using fixtures and a Kinesis of Name in a sense to keep things dry between the back end and the front end, or would you consider some sort of bridge necessary?
I really consider something other than fixtures because fixtures are one thing that you have to use everywhere. Fixture scenarios might be a better choice there, so you can choose the scenarios. I know within our Selenium tests that we run, it's not quite what you're talking about, but it is an end-to-end thing. We use fixtures for a lot of that testing, but there's times when I want to test this particular user in this particular configuration, but it's not a configuration I want to leak into all my other tests. We have special Selenium callouts that says build up this user with this configuration, build out this user with this configuration. So when at the start of a test, we'll actually go and run that user, run that Selenium setup, and it'll set up that specific scenario for that specific test. And that has actually worked pretty good for us. So yeah, even in that scenario, I would stay away from fixtures as much as you can. That special setup is really important. Yes?
Do you think a lot of the kinesis, the preferring kinesis of name versus like position, it seems like a lot of it boils down to being as making your code as transparent about what it's doing as possible, and sort of being able to more quickly see, and maybe that feeds into our guts when we look at code and it's like the definition is spread in so many different places and it's not obvious how it's tied together. It seems like the problem with coupling, when we run into problem with coupling, is when the coupling is not explicit, when it's not clear. We need coupling. It's necessary for running programs.
Right.
The problem is when we can't see it.
Question is, do I think that the explicit nature of the naming helps us read the code better, and that kind of feeds into our gut? I think our gut is trained by experience of writing code that doesn't work. I think it was Kent Beck that said all process is driven by fear of what has failed before. I think our gut is trained by fear of what we have seen before. Oh, when I do this, it breaks and I don't like it. So I have a visceral reaction to that. I think it's more of the training thing. I think being explicit kind of feeds into that because we can see it and it's apparent to us. But I think there's a lot of training that goes on. And I think that's why a lot of times, if you don't have a developer who is concerned about the craft of programming, they have actually probably trained their gut to be resistant to some forms of kinesis and bad development practices that you and I would go, don't do that. They've just trained themselves to, oh, well, this is the way the world is, let's just kind of plow through it. So I think it's a training issue.
Something you didn't really address but is related is once you get to the point where you have some amount of Kinesis of Name, reducing the amount of that you need by simpler interfaces.
Yes. I know that's a big thing that you promote is defining your interfaces and keeping your interfaces narrow. You've reduced the number of names that you have to deal with between two section programs. So it's not just reducing the strength of Kinesis in the type of it, but also reducing the
Degree of kinesis by reducing the number of names. Yeah, both of those techniques absolutely useful in developing good modular software. Okay. Thank you very much.